In this lecture, we will be examining the integration and differentiation of Taylor series. Recall, given a function f with derivatives of all orders throughout some interval containing a, think interval of convergence, the Taylor series generated by f at x equals a is given by the following expression, and we have the first several terms written out here. If a is 0, we call the series the Maclaurin series. Also recall from our studies of power series, we have a result for the differentiation of power series. So if we have a power series representation of f of x on an interval of convergence I, so f of x is actually equal to this power series for any x chosen from I, then for all x in that interval of convergence I, we can take the derivative of both sides of this expression, where the differentiation done in the power series is done term by term. We can see that here. We're just doing power rule term by term. Going the other way, we can do an antiderivative or an integral. So we have the same setup. Power series equals this function on the interval of convergence I. And if we want to take the integral or the antiderivative of both sides here, we can take the integral or the antiderivative term by term in that power series. We see here the general expression, the reverse power rule for computing an antiderivative, and here you can see it done term by term. Well, recalling that a Taylor series is a type of power series, this is nothing more than a power series with a very specific coefficient, C sub n here. So these results for power series apply to Taylor series. So let's look at an example of this. One example, let's take a look at the Maclaurin series for cosine of x. So recall this is our Maclaurin series for cosine. So we have an alternating series that picks up the even terms, even powers of x. And we, of course, know what the derivative of cosine of x is. We know that the derivative of cosine of x is minus sine of x. But let's check that. So we know from our power series differentiation theorem that we can take the derivative of both sides of this expression, and the derivative of the power series can be done term by term. So that means when we take this derivative, we will have minus 1 to the n, and then we have to do our power rule on x to the 2n. So the 2n comes out front, and then we reduce the power of x by 1, 2n minus 1, and we still have that 2n factorial in the bottom. And we need to decide where we start our sum, and we note the derivative of that first term, of that 1, is going to be 0. So the first term that will show up in our derivative here will be the term associated with this x squared over 2 term, which is going to be an x term, x to the 1 power. So it looks like the first term we want to start where n equals 1, because that power of x would be x to the 2 times 1 minus 1, or x to the 1. So this gives us the derivative. We can simplify things a little bit, noting we have a 2n in the numerator and a 2n in the denominator. So let's pop the top term off of that factorial in the denominator. So we can rewrite that as 2n times 2n minus 1 factorial, and when we do that, we see the 2n's cancel. And so our result is the sum n going from 1 to infinity of minus 1 to the n, x to the 2n minus 1 over 2n minus 1 factorial. And of course, we know the interval of convergence for the Maclaurin series for cosine of x is the whole real line. So this works for all x in the real numbers. Let's actually look and see what we have here. Let's look at the terms. So when n equals 1, we get negative 1 to the 1, x to the 2 times 1 minus 1, or x, over 2 times 1, or 2, minus 1, over 1 factorial. So we have a negative x. When n equals 2, we get minus 1 squared, so we get a plus, x to the 4 minus 1, or 3, over 3 factorial. When n is 3, we get minus 1 cubed, so we get a minus, x to the 6 minus 1, or 5th, over 5 factorial, and then the next will be x to the 7th over 7 factorial, so on and so forth. And notice that what we have here, let's factor out a minus 1. We have negative quantity x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth. And we recognize here that this was the Maclaurin series for sine of x, and so we see that we have minus sine of x here, which confirms what we already knew, but we can see that via differentiation of the series, the Maclaurin series for cosine x, we can get to the same result. Now also note that there are different ways you can do this problem. We started with the general formula for the summand and differentiated it in terms of n. And then that gave us this new Taylor series for minus sine of x. You can also write out the first several terms, differentiate them term by term. So if you had looked at this, you would say, okay, derivative of 1 is, with respect to x, is 0. The derivative of this term would have been minus x, which you get here. The derivative of this term would have been 4x cubed over 4 factorial, or x cubed over 3 factorial. So you could have gone through term by term and then written down the summation, figured out how to write your answer in sigma notation. Either way, you want to end up with your answer in sigma notation, and it's fine to do it either way. You can work with this original sigma notation expression itself, or write out the first several terms, do your differentiation, and then try and find the pattern. It's really just a matter of personal preference. But again, with this exercise, we were able to see an illustration of how this differentiation of Taylor series works via confirmation that the derivative with respect to x of cosine of x is minus sine of x. Let's look at another example, but first, let's introduce a couple other important Taylor series that come up a lot. So for these Taylor series, for all x in the open interval minus 1, 1, we have natural log of 1 plus x is equal to this series here. So the alternating series of x to the n over n. And arctan of x is an alternating series of x to the n 2n minus 1 over 2n minus 1. Looking at these a bit more closely, this natural log of 1 plus x series, it looks similar to the Maclaurin series for e to the minus x, if we subtracted 1. And the arctan series looks a lot like sine of x. But the key thing to recognize is the terms in the denominator. these are not factorials. Because you have this x to the n in the top over n in the bottom, instead of n factorial, you end up with a finite radius of convergence. Basically, n is not going to infinity fast enough to make a difference in terms of what x to the n will decide for the interval of convergence. Same kind of thing here. Because you lack a factorial, the denominator is just not getting big enough compared to, say, the series for sine or e to the x. But these are very, very common Taylor series that come up in application. Natural log of 1 plus x, actually, this comes up a lot. This is a very foundational tool in the area of mathematical finance, specifically when you're modeling asset returns. But let's see an example of this. So suppose for x in minus 1, 1, we want to compute the indefinite integral of natural log of 1 plus x. And we're going to use the fact that here is our series for natural log of 1 plus x for x in minus 1, 1. And we can integrate term by term. So we can see that written out here. And for this question, let's do it integrating term by term and then finding the pattern. So here we have an antiderivative of x dx. So we'll have x squared over 2. And of course, each one of these indefinite integrals will give rise to a plus c. But we can lump all of those together into one. So why don't we include that here in the beginning? So this will be c plus, we have x squared over 2. And for this term here, we'll get a negative x cubed over 3 times 2. For this term here, we'll have an x to the 4th over 4 times 3. For this next term, x to the 5th over 5 times 4. For the next, x to the 6th over 6 times 5. So on and so forth. And it looks like we can identify the pattern. So we have a constant, and then we'll have a sum. We'll have to figure out what we want n to start at. And it looks like we have in the denominator, we have the power of x times one integer smaller. In each case, x to the 4th over 4 times 3, x to the 5th over 5 times 4. Maybe we should throw in 2 times 1 here so we can see that pattern. So it looks like what we have is x to the n over n times n minus 1. It's alternating, so we have to think of the power of minus 1. And where do we start n? So let's pick the starting value for n first. The first term has to be the x squared term, so let's start at 2. And the first term also has to be positive, so we want the first term to have a minus 1 to a positive power. The first term is 2, so minus 1 to the n should do it. Then we can check that we got it right. If n equals 2, we get minus 1 squared, x squared over 2 times 1. Yes, we got it. For n equals 3, minus 1 cubed, so a negative, x cubed over 3 times 2. So it looks like we got this correct. So we now have this power series representation for the antiderivative of natural log of 1 plus x dx on that same interval of convergence. Now, this is just a summary of what we just established. And reminding ourselves here, this is our series for natural log of 1 plus x. But let's actually think about confirming this, because we actually know how to integrate. the natural log of 1 plus x dx. From our single variable integral calculus experience, we are not doing the computation here, but integration by parts will give you this result. So the integral of natural log of 1 plus x dx is 1 plus x times natural log of 1 plus x minus x plus c. Let's actually check what happens if we take our series for natural log of 1 plus x and plug it in here. So if we do that, we get 1 plus x times this expression here, or x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5, so on and so forth, minus x. So don't forget our other terms outside here. So we now need to FOIL this out. So our first term, we will have 1 times everything in this expression. So this expression just gets copied down. So we have an x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5, so on and so forth, plus what we get when we multiply x by every term in this expression. So take every x and increase its exponent by 1. So we will have x squared minus x cubed over 2 plus x to the 4th over 3 minus x to the 5th over 4 plus x to the 6th over 5, so on and so forth. And then we still have our minus x plus c at the end. And now we want to see how we can simplify this. So first note that this x and this minus x will cancel. Our plus c will stick around. And now we need to pair things up by powers of x. So for instance, here we have our x squared term, and here we have our x squared term. But we need a common denominator of 2. So let's multiply this by 2 over 2. When we do that, we will get 2x squared minus x squared, which is x squared over 2. For the x cubed term, we need a common denominator, which will be 2 times 3. So this term here, we need to multiply by 3 over 3, and here we need a 2 over 2. When we do that, the result is a denominator of 6, and we have a 3x cubed, a negative 3x cubed plus 2x cubed, which results in a minus x cubed over 6, which we should leave as 3 times 2. For the x to the 4th term, we see we need to get a common denominator of 12, so we multiply by 3 over 3 here and 4 over 4 here. So the result, we have a denominator of 4 times 3, and we have a minus 3x to the 4th plus 4x to the 4th, or plus x to the 4th. And you can see here that we are building this series, which we obtained by term integration of that Taylor series for natural log 1 plus x. So this is an illustration of how we can sync this integration of Taylor series up to our knowledge of integration from our previous coursework, in particular, in this case, the technique of integration by parts. So all of this work illustrates to us that when we have a Taylor series representation of a function, we can integrate them term by term or differentiate them term by term, and the new resulting series will be valid on the same interval of convergence for the original series.